My name is Campbell Mutert, and this is my video lab for Physics 1 for constant velocity. The purpose of the lab was to use Tracker to observe the motion of an object traveling with a constant velocity, use that data to construct a glow script model based on Newton's second law to describe the observations, and then to compare the two sets of data in Excel. The main finding was that the glow script model overestimated the velocity of the ball towards the end of the observation period. The fundamental principles represented in this lab are Newton's first and second laws. The first law explains that an object's motion won't change without an external force, and the second expands on that to say that the resulting change in motion is directly proportional to the magnitude of the force that was applied. This is expressed as F net equals mass times acceleration, which is equal to the change in momentum over the change in time. Newton's second law can be rewritten as the momentum principle, where the final momentum is equal to the initial momentum plus the sum of the acting forces times the change in time. Since momentum equals mass times velocity, you can divide by the mass to reach the velocity update formula. When an object moves with the same speed without changing directions, velocity is constant, so the final and initial velocities are equal. This means that for velocity update formula, F net has to be equal to 0 because m and t are already defined. The velocity represents the ball's change in position from frame to frame, which can be used in the position update formula to predict the ball's position at future time t. The system here is the object in motion, which is the ball. The surroundings include the air and the floor, but we assume that there is no air resistance or friction that could result in a change in velocity. Because the surface of the floor is flat, we assume that there is no acceleration due to gravity and thus only observe changes across the x-axis. For the tracker observations, I placed a ruler on the wall and used it to calibrate to 10 centimeters. The origin of the ball is at 0, with positive x being to the right and positive y upwards, and the initial time is 0 seconds. Since the frame rate of the video was 0.033 seconds, that's the delta t that I used. The initial velocity I calculated was the change in position over the change in time for the first two frames, which was approximately equal to 1.604 meters per second. So this is what the ball's motion looked like in Tracker. The red markers are where I estimated the center of the ball's mass to be at different time points. And this is what the computational model describing the ball's motion looked like. The yellow sphere is the ball and the black sphere is the origin. This set of code is for the background, the colors, and the graphs. I started by defining the ball's mass as 0.204 kilograms and input the initial position and velocity that I calculated earlier. The initial time was 0 and the time between frames was 0.03 repeating seconds. I set the loop to run until t reached 0.67 seconds because that's how long my tracker observation period was. Because we assumed constant velocity, F net was set equal to 0. The new velocity was calculated using the velocity update formula, and then the new velocity was input to calculate the new position vector. Then these were used as the initial position and velocity at the next time t. The last two lines printed the data so I could export it to Excel for analysis. This time versus x position graph in Excel. The pink line is the model prediction and the green line is the observed position. At first, the model and observed position are very similar. However, at later time points, the model increasingly overestimates the x position of the ball. This is likely due to the fact that the model uses an F net of 0 in the calculations. Because the observed position is less than that, we can assume that there is a force present that's causing the ball to decelerate, which in the case here is probably friction from the floor. Finally, a graph of the average velocity seems to have a cyclical pattern that is not present in the model's graph. It could be because the ball I use is not a perfect sphere, so the ridges and texture of the surface led to different interactions with the floor due to variation in the points of contact. For the what-if question, if the x-axes were flipped, the ball would roll into the negative x direction. However, the distance between points wouldn't change, so the magnitude of the velocity wouldn't either, just its direction. The computational model would still overestimate, but it would predict that the ball would be further to the left. For the what does it mean part, no, it is not possible to determine the number of forces that add up to 0. A situation where F net is really 0 is unlikely because every single interaction would have to add perfectly to 0.